Hi, I'm Wim Bogaerts from Ghent University and IMEC, and welcome in this tutorial about programmable integrated photonics. Let's focus on the first two words as an introduction, programmable and photonics. When we think about programmable things, you think about devices that can be configured in software, where the functionality is adaptive. When you think about photonics, you think about manipulating light on a small scale. So programmable photonics brings these two elements together for manipulating light in software on a microscopic scale. And if you ask yourself, why do we want to do this? Well, light contains information. And so processing light means processing information. So the traditional ways of manipulating beams of light is using discrete optics, lenses, mirrors, polarizers, spatial light modulators. Now, if you want to scale this up in complexity, you quickly run into problems. And that's why we're moving to programmable integrated photonics. We integrate photonic functions on a chip. And with these functions, we mean light sources, waveguides, filtering, modulation, detection. If you throw all of that together and connect these functional blocks with waveguides, you get a photonic integrated circuits. And the functionality of these circuits, just like in electronics, scales with the number of components that you can interconnect and the complexity of the interconnections. So in the end, if you want to make a complex circuit, you want to go to a large number of components. So that brings us to silicon photonics. Silicon photonics is the technology that allows you to integrate thousands or even 10,000s of components for optics on silicon with a very high integration density. And the advantage is that you can fabricate those components with the same technology as CMOS electronics. And that gives you two scale advantages. On one hand, you have the large-scale manufacturing of the CMOS industry. On the other hand, you have submicron scale waveguides that allow you to really compress the size of your photonic circuits. And as a result, over the past decades, we've seen a steady growth of complexity in silicon photonic circuits, with increasing numbers of integrated components in the same circuit. Now, if you look at this graph, which you could interpret as a kind of Moore's law for silicon photonics, you should realize that all of these dots on the graph are application-specific circuits. They're circuits built for one particular application. And that has certain consequences for the widespread use of photonics. Let's take an example. If you want to make an optical transceiver for a data center connecting 2 points, you need to go through the phases of design, fabrication, packaging, and testing of a photonics chip. So if you pick a protocol, for instance, parallel single mode fiber, you have to build a circuit with 4 modulators that encode the outgoing signal and 4 photodetectors that take the incoming signal from 4 fibers. However, if you want to change protocols for transmitting the same amount of information on, for instance, a coherent link, you need to build essentially a new circuit using the same type of modulators and the same detectors. You just have to configure them now into an IQ modulator and into a coherent receiver. And if you want to use the same modulators and detectors for instance, a wavelength division multiplexing link, you have to redesign the circuit again, this time integrating some wavelength multiplexer and demultiplexer, and building your new circuit. Every time you have to build that new circuit, you have to go to design, fabrication, packaging, testing phase, which can easily take you a year and like 500,000 to €1 million. So this is a very costly proposition if you want to develop a new product and if you're critical in time to market. Compare that to how you prototype things in electronics. Typically, if you have a new idea for an application, you just start off with off-the-shelf electronics, which can be programmed, like a field programmable gate array or a digital signal processor. And after a couple of weeks, you have a tested chip and you can try it with your customer and see whether your idea works. And if it works, in that case, you can tape out an ASIC if you want. But in the meantime, you have taken one of these field programmable gate arrays, you've connected all the blocks together in software, and you've tested the idea. So the question is here, where is this equivalent in photonics? Where are the photonic FPGAs? And people have been coining different names like programmable photonics or reconfigurable photonics or photonic processors. I think the definition which is very important here in this context is a photonic integrated circuit that can be reconfigured in software to perform different functions. And all of these three elements are important. So what would such a photonic processor look like? Well, as a black box, it essentially takes optical signals going in and out, but it can also process a high-speed electrical signals or microwave signals, because optics has a massive bandwidth and is really good for filtering and frequency conversion of this kind of high-speed signals. If we look in a bit more detail, again, you see your box, your optical interfaces, in this case I've drawn at the top. Your electrical interfaces for your high-speed signals are essentially nothing more than a modulator that immediately converts your electrical signal into an optical signal. And at the output converts the optical signal back to an electrical signal. And internally, everything is in the optical domain. And the magic block, that blue block in the center, is a programmable all-to-all scatter matrix. This essentially has the capability to couple all your ports to all your other ports in any type of linear combination. Now, such a scatter matrix can be wavelength dependent, it can include reflection. The whole point is that you, by programming that scatter matrix, you can reconfigure the functional blocks of your circuit. Now, such an all-to-all scatter matrix is kind of complex to start with. That's why today we see a lot of programmable circuits that are a simpler form, that basically separate the inputs to the outputs, and you only have propagation in one direction through your circuit. This kind of forward-only circuits were already proposed in the 90s, but it's only in like 2013 that David Miller of Stanford came up with the idea of implementing and configuring these circuits. Essentially, you can configure such a circuit from just a few simple building blocks that you cascade. And in this case, in this triangular lattice that we show here, the building blocks are a tunable coupler and a phase shifter. And these together form what we call the basic unit cell of a 2x2 unitary gate. In its most generic form, this unitary gate has two inputs, two outputs, and it performs any unitary or lossless linear combination between the inputs and the outputs by tuning the coupling and tuning the phase delay between the different waveguides. The easiest implementation for such a unit cell on a waveguide circuit is through a Mach-Zehnder interferometer. Essentially, you split your light, you use one phase shifter to control the phase delay, and that in turn determines the coupling ratio of your gate. If you want to control both the coupling ratio and phase, you need to add at least one additional building block here, so an additional phase shifter. But this is a very simple implementation. With this block, by cascading them, you can build much larger circuits. And we've seen different circuit architectures for these forward-only circuits in the past couple of years. On the left side is what we call a Clemens type structure, which is the most compact way of constructing an arbitrary transformation, while on the right there's a triangular mesh, which is also proposed by Reck and Miller, which is the easiest to configure. And that's why the first demonstrations of such waveguide circuits were essentially in this triangular meshes. So this is the first programmable photonic circuit that got demonstrated. It's made in silica, so it's quite large, and it consists of a 6x6 interferometer. The first demonstration in silicon, which was much smaller in size and was only a 4x4, was done by our group in Ghent, which showed a universal coupler. And then a year later, we already see a much larger version demonstrated by MIT with 26 inputs and 26 outputs. So now, why would you want to use these forward-only meshes? Well, they give you a lot of functionality, which is very, very useful for quite a lot of applications. If you consider the set of inputs and set of outputs as a vector of complex amplitudes, so intensity and phase, then the circuit itself acts as a matrix performing a real-time matrix multiplication of a matrix vector multiplication. And these kinds of matrix vector products or multiply accumulate operations are used a lot for pattern recognition algorithms, for quantum optics, and for artificial neural networks. And that's why over the past couple of years we've seen quite a lot of papers demonstrating these circuits in quantum optics, but also in accelerators for artificial intelligence. However, while these circuits are all nicely programmable and quite flexible in their functionality, they are always designed for one particular purpose, doing these multiply accumulate operations. So they are programmable, but they're not generic. They're still application specific circuits. If we want to build a really generic processor, we need to step away from these forward only meshes and go to these omnidirectional, like all-to-all scatter matrix. So how would you implement one of those? Well, the solution was proposed already like 5 years ago using meshes consisting of waveguide loops. And for the first example is this square mesh of loops, which allows you to couple all these waveguides together, but you see that the ports are still divided between a set of input ports and output ports. To basically couple all ports to all ports and make the whole mesh universal, you need a hexagonal mesh. And that allows you to basically implement any unitary scatter matrix. And this becomes interesting now because you can use such a mesh to route light around. So you can basically, by reconfiguring the couplers between bar and cross state, you can route the light around the mesh. You can do that for multiple routes, and you can even bring two routes together through the same coupler. And that allows you to make crossings, for instance, or even to make power splitters. And if you take two of these split beams and combine them again, what you get is, because everything is coherent, you get an interferometer. And unlike the forward-only meshes, the recirculating meshes make it very easy to implement a delay line. So you can build filter circuits like a Mach-Zehnder interferometer or even a ring resonator by routing your light into loops. So this is quite flexible. You can do routing, you can do filtering, you can do power distribution. Now, the first demonstration of such a circuit was done by the Polytechnical University of Valencia in the group of José Capmany, where they built a 7 hexagonal cells, programmable circuit. And already this small circuit allows you to do 100 different functions. For instance, you can do different delays by just routing through different edges. They've also demonstrated that these circuits can essentially perform the same forward-only functions that you can do with a specialized forward-only mesh. So for instance, this is a C-NOT gate. But you can also do filters, like a double Mach-Zehnder or this cascaded double path filter. And because every element in this circuit is tunable, both in phase and in amplitude, you can configure the extinction ratio and the bandwidth of these filters. You can do the same for resonances, like a ring resonator. You can tune the extinction ratio, the resonance frequency, and the bandwidth. There are some limitations though to filters. If you have filters in a fixed mesh, obviously the delay length that you can implement is fixed by an integer number of these edges of the cell. So for instance, for a Mach-Zehnder interferometer, you always have an even number of edges. And that limits the free spectral range that you can get from your Mach-Zehnder interferometer. Similarly, for a ring, the smallest ring you can make consists of 6 of these edges. So that's already a quite long ring, and therefore will give you a quite small free spectral range. So if you want to build filters with a very large free spectral range, that means that you have to make these edges as short as possible. And that requires sharp bends, short phase shifters, compact splitters, dense packing. Essentially all the properties that you find in silicon photonics. And that's why silicon photonics is still the most likely technology to build these recirculating universal circuits. So if we want to scale this up from 7 cells to many more cells, there's different ways to do it. You can take your hexagonal mesh and you can scale it up in every direction. But you can just as well take the same unit cell and do an anisotropic scaling, for instance, in a rectangular form. Depending on what your requirements are in terms of losses and number of I/O ports that you want, one of these forms can be beneficial. A good characterization, for instance, is to calculate the longest shortest path, which is kind of a contradiction. It's essentially the shortest path. You measure the shortest path between in any pair of ports. You calculate the shortest path, and from all these shortest paths, you take the longest one. And as your mesh grows, this longest path or longest shortest path will obviously also grow. Different mesh configurations will scale in a different way. So the radial mesh, which is indicated in red in this graph, has the lowest loss accumulation if you start growing the mesh. While a rectangular mesh with a fixed dimension on one side will have, instead of a square root like accumulation, will have linear type of accumulation, which is much more severe. If you look at, for instance, on the other hand, to, for instance, the number of external ports, then you see that a rectangular mesh gets more external ports. So if you want to have a mesh with a lot of ports to manipulate, then a rectangular mesh might be more attractive. So now that we have some idea of how you can scale this mesh, what are the limitations? What do we need to make this work? Well, first of all, it's clear that we need really good components for these 2x2 gates. They need to be compact, short, and also have a low optical loss and low electrical power consumption. And then you need many of those. So let's first look at the way to implement these gates. Just as a reminder, what is the basic functionality that we have here? Well, the essential element for this 2x2 optical gate is a phase shifter and a tunable coupler. And we already know that we can build a tunable coupler out of phase shifters. So a good, efficient phase shifter is the key component to make this work. If we think about silicon photonics, what is the typical way to implement such a phase shifter? Well, it's a heater. You basically take a waveguide and then you add an electrical resistor nearby, like above it with a metal heater or next to it with a doped silicon heater. Now, these are quite simple to make. They're fairly efficient in silicon because silicon has a high thermo-optic coefficient. But they complicate matters a bit because, well, the response curve is quadratic. So just changing your voltage linearly will give you a quadratic phase shift. And worst of all, heaters get hot. If you scale this up to thousands of heaters on a chip, this is going to be a problem in terms of thermal crosstalk, in terms of power consumption, in terms of cooling. So what are the alternatives to heaters? Well, a typical alternative in silicon photonics is carriers. Carriers are used for modulators and they give you a fast modulation. However, the effect is quite weak, so you need a long device, which is not what we want. And it also induces losses, which is also not what we want. So we need something else. Liquid crystals is something that we've been exploring, and that has a quite strong birefringence. So you can modulate or you can tune it with quite a low power and in a short length. And another technique that we're using is MEMS. Finally, the last one on the list is the Pockels effect, which you'll find in specialty materials like polymers or perovskites. Especially this last one has been a lot of effort invested, and it's a very hot topic at the moment to make a high efficiency Pockels effect based phase shifters because they're the ideal phase shifters. And for instance, the work from IBM in Zurich, which is now part of the company Lumiphase, has shown really high quality phase shifters based on the Pockels effect. One of the things that we're looking into is liquid crystals, which basically reorient themselves when you apply an external voltage. And so in some recent work, we've shown a quite high efficiency liquid crystal phase shifter by putting an electrode very close to the side of the waveguide. And therefore we can switch the liquid crystal right next to the waveguide where you still have a high optical intensity. The challenge is to get that liquid crystal integrated with the silicon. So we make these little cavities where we can do little droplets of liquid crystal. And then if you apply a voltage, we do observe a quite good phase shift on the order of 0.8 pi over a length of 50 microns. The second mechanism that I mentioned already that we're working on is MEMS. Now MEMS and photonics are, especially silicon photonics, are a very attractive combination because they're both made in silicon, and moving silicon as a material around has obviously a very strong optical effect. Now, usually the problem is that with MEMS, it's not that easy to integrate it with all the other functionalities in a silicon photonics platform. And that's what we're trying to do in the European project MORPHIC, which is a collaboration of 6 partners within Europe, is to try and integrate MEMS silicon photonics together with all the other silicon photonics functions that are already been proven, like modulators and photodetectors. And with quite some success. So for instance, this is an example of a MEMS tunable coupler where we essentially just move the waveguide vertically to bring waveguides closer together or further apart so we can change the coupling. Or for instance, this MEMS phase shifter where we move the waveguide or a silicon beam close to the waveguide laterally by pulling at it with a comb drive. With these tunable couplers and phase shifters, we can make these universal 2x2 gates. So that's exactly what we've done, and this is a circuit that's up till now not been characterized, so it's a bit of a preview. It shows you 24 hexagonal cells using MEMS phase shifters and MEMS tunable couplers. In total, it requires 200 separate actuators to make it work. And I'm showing you this because it highlights one of the problems that we had on our scaling slide. If we have these many, in this case 200, but we want to scale this up to more, if we have these many 2x2 gates, they all need to be controlled electrically. So that means that for every phase shifter and tunable coupler, you need some digital driver, which requires electrical circuits, but it also requires a connection between your electrical circuit or your electrical driver and your photonics chip. And bringing electronics and photonics together is not that straightforward. There are different ways to do it. Monolithic integration, where they're on the same chip, is in the long term the most attractive, but it still has quite a lot of complexity in terms of processing and in terms of trade-offs. So at this point, the most flexible technique or powerful techniques seems to be flip chipping or 3D stacking. But that's again quite costly, and it requires quite a lot of problems in terms of co-design of your photonics and your electronics. So that's why for most experiments people today still rely on wire bonding, and that limits the number of connections that you can actually use. Now the second problem, apart from how you connect all of this together, is how you drive this. In this driving scheme where you have a digital controller but an analog driving signal, you always have some errors. You have discretization steps of your digital to analog converter, and you have variability in your transducer curve of your heaters. So in that case, you always add up errors. And it becomes more complicated because if you are driving multiple heaters together, that quadratic response curve makes your life quite difficult. For instance, if you have 2 heaters in the same Mach-Zehnder interferometer and you want to drive them both together, that together they induce a phase shift but they don't change the coupling, so essentially you want to drive them with the same phase shift but maintaining a fixed delta phi, a fixed phase difference, you have to drive one heater, for instance, in a linear curve, but the other one has to go through a quadratic curve. And these need to be very carefully characterized for it to work. So the quadratic response curve of a heater actually complicates matters a lot. So you always need to keep in mind that you have this quadratic curve. That's why it's sometimes useful to switch your analog driving for digital driving. For instance, using pulse width modulation. And there the power delivered to your heater is just proportional to the duty cycle. So now you have a linear driving scheme. The key requirement here is that you drive this fast enough, because your heater is a fairly slow device. So if you modulate these pulses fast enough, what your heater feels is an average power delivery. And that's you see for, like for instance, frequencies over 200 kilohertz, you see that the heater has essentially a uniform response. Now, if you have driving that's only one part of the equation. How do you know whether you're driving everything correctly, especially in a complex circuit with hundreds of heaters or MEMS or liquid crystals? Now, that means that you have to combine your driver circuits with some readout circuits and some control loops. And these control loops can be either in the analog domain as a digital loop, for instance, using a digital signal processor or an FPGA, or you can run it at a very high level in software. Now, obviously, the analog loops will be the most efficient and the fastest. Now, for that to work, you need monitors. And these monitors preferably don't absorb a lot of light. They're just there to observe how much light is in the circuit, but they shouldn't affect the performance of the circuit too much. So you can do that with different mechanisms like tapped waveguides, like with detectors, or even very short inline photodetectors that only absorb a fraction of the light. Or you can use these fancy detector schemes like clip or integrated heaters, like I'm going to show you. For instance, one way to build these monitors is to have an erasable directional coupler. You have a directional coupler that taps off a bit of light, but then afterwards, after you've configured your circuit, you can, by an annealing step, erase all these extra couplers. And that allows you to do a one-time configuration of your circuit. So this technique, which has been demonstrated by Cornerstone in Southampton, could give you access to one-time programmable circuits. Another type of monitor, for instance, is clip monitor, which essentially is mounted on top of your waveguide, and it measures the losses that are already intrinsically there in your waveguide, which gives you rise to a small amount of free carriers, which can be measured using a resonant RC circuit. Or you can use that same type of absorption to measure the resistance of the waveguide directly, for instance, by running a current through it. And the interesting thing of this technique, which was by the University of British Columbia, is that you can integrate this monitor directly in the heater. So the resistor can be a heater, but at the same time measuring the resistance gives you a monitoring of the amount of power. Now, if we have monitors, if we have actuators like phase shifters and tunable couplers, we can build these feedback loops. And the simplest feedback loop it's easiest to illustrate on a single 2x2 gate. So say, for instance, that we have this 2x2 optical gate, and now we can add this feedback loop. Say that we want to put or to direct all the power into the bottom output port 2. Then essentially we can tune the phase to bring these two inputs in antiphase, which couples all the power to the bottom port. So we minimize the detector power to maximize the power in the bottom port, and then we do the same thing by tuning the coupling, which basically balances out the coupling and brings all the power to the bottom port. And now we can cascade this routine into, for instance, this 4-port circuit, and now we can step by step configure every gate to couple all the light to one output waveguide. And as a result, by systematically cancelling out every step, we get all the light in the bottom waveguide. Now, of course, these detectors need to be transparent, because otherwise the rest of the circuit is useless. But if these detectors are transparent, we can just as well add a next stage and a next stage. So we basically add different rows of circuit functionality that can each be independently configured. And as a result, you can implement a beam coupler that can couple 4 beams into 4 different outputs. And this is something we demonstrated with this particular circuit already 5 years back, where we just hover a fiber over the 4 inputs, and the circuit adjusts itself in such a way that all the light ends up at one output port. And the nice thing is that these optimization algorithms, you can let them run continuously. So essentially the circuit adapts itself to the changing input. This is another example, this time by the Polytechnical University of Milan, where they mix up 4 input modes and then use a circuit to unscramble the 4 inputs into 4 different output waveguides. Now this is a kind of easy algorithm that can be locally run, but for more complex configurations, you have to think about different types of algorithms, and you can think about machine learning algorithms, genetic algorithms, etc. Now, not all algorithms work sufficiently fast to configure such a circuit. So this study from Stanford University compared different setup algorithms and how they converge and how fast they can be run on these forward-only circuits. Now, for forward-only circuits, light only flows in one direction. But for a recirculating mesh, your control layer will probably be a bit more complicated. Now you do need to couple between your monitors and your actuators, but where would you put your monitors? That's the first question, because now your light can flow in two directions. So you have to monitor the flow in both directions. You have to somehow monitor phase and amplitude. Where do you put your monitors? This is not yet an answered question, because if you have to monitor everything in such a circuit, that means you need like 8 monitors per gate, and that's quite a lot. So you need to come up with design techniques that allow you to optimize your circuit without having to have a massive amount of monitors. So if you have that control layer that does the local control, there's a lot of higher order functionality that you still have to design. For instance, how to configure a circuit. And once that circuit is configured, how do you use high-level control algorithms that make sure that the circuit keeps functioning as it should? That essentially creates an entirely new set of design algorithms. Rather than in the past designing a layout like we did here, where we just draw the shapes that have to be fabricated, or even go into these kind of building blocks and construct a circuit that is fabricated, we now have our fabricated circuit. We need to figure out how to configure it and which code we need to run to make sure that the circuit behaves as it should and keeps behaving as it should. And this is a completely new field. This essentially creates an entirely new class of design IP, which already exists in electronics, but is new for photonics. Like how to translate a circuit description into a configuration that can be programmed on a chip. What are the necessary control routines? And later on, we can bring these together into reconfigurable blocks that can then be used as a cell, a unit cell inside custom chips that we want to use. Just like today, you can take an ARM processor core and put it on your own system on chip. So these algorithms, these design routines, they're still very, very young. There's not a lot out there, not a lot of design routines out there for such programmable circuits. One example of such a routine is to use graph descriptions. So this is used a lot in networking, network architectures, but for representing such a circuit, you need to come up with a graph description that respects the laws of physics. So what we came up with in the end, that the flow of light, to respect the flow of light, is that every tunable coupler is represented by 8 nodes and 8 connections. So that's quite a lot. But still, these circuits are relatively modest compared to some larger circuits or larger problems that are used for graph algorithms. So it's still okay. And once you have such a representation, you can then apply graph routines, for instance, like routing with obstacle avoidance or collision avoidance, or distribution problems where you impose different conditions. Like for instance, in this case, we have different congestion costs. Here we try to minimize the number of ports that we use, while there, on the far side, we try to minimize the power that's in every individual waveguide. Now, once you've programmed this and you have come up with a good configuration, you're not there yet. Because, as we saw earlier, our control over every individual actuator is not necessarily perfect. You have always discretization errors. So what happens in such a mesh if your couplings are not perfect? Well, what you get is like a kind of parasitic paths. And because your mesh consists of loops, you get parasitic ring resonators. And this is what we see if we just route through such a mesh, but we add a 1% random variation, is that you already see these visible resonance fringes appearing in your transmission spectrum. And with a 3% random variation, the resonances are totally unacceptable. Luckily, this is not as big a problem as it looks, because we do have quite some programming freedom in this mesh. For instance, we can program all the unused couplers in such a way that we kill the resonances as much as possible. And that way we still have our insertion losses because of the parasitic coupling, but we don't have these annoying fringes anymore. So these routines are essential to make things work. So we're not just looking at hardware, a chip that gives you optical and electrical connections, but also the software layers to configure everything. So this, in the end, could look like something like this, where you integrate your electronics, your photonics, and your RF ports into a small compact package. And attached to that, you have your software layers, your design kits, and your debug tools that allow you to configure such a circuit. So this complete technology stack needs to be built. Before we have every layer filled into a decent level, we cannot yet use these multifunctional circuits. So if we get there, we would end up with something like this, a generic programmable optical processor, where you have your optical ports, your RF ports, your functional building blocks in there. What can you do with it? Well, let's look back at our original problem, our programmable transceiver. So we can now basically take our 4 fiber input and outputs and route them in such a way, for instance with the Mach-Zehnder modulator configured there, that we get a PSM4 transceiver. And we can, at the receiver side, we just have to wire up the fiber ports to the right detector. But we can very easily reconfigure this circuit to build a coherent modulator. So for instance, we build a splitter, we route our paths into an IQ modulator where we do a nice path balance, and then we basically send it to the output fiber. And we can just as well get a 90-degree hybrid, because we can just tap off our laser as a local oscillator. And for wavelength division multiplexing, okay, we need 4 lasers, but we can then build a ring resonator based multiplexing circuit to bring all these wavelengths together. And the same thing, the same type of filters can be used at the output. But we're not limited to these transceivers. The idea was to build something that's truly multifunctional. So we can, for instance, use this kind of circuit to implement a switch between 8 fibers in and 8 fibers out by just rerouting the light the way we want it. Or we can make a beamforming circuit by splitting your light in a path balanced splitter and then routing your light to the modulators and then to output fibers, taking into account that we indeed have to balance all the paths. Or last but not least, we can have, for instance, a microwave circuit where we modulate an RF signal onto our optical carrier and then use an interferometric circuit to reconstruct the signal at the output. And if we add a filtering circuit in the middle, we can basically correct the signal or improve the signal. So such circuits like the microwave circuit could be very useful in, for instance, fiber to the home transceivers, where you can encode ADSL signals on top of your fiber signal, or you can do radio over fiber for 5G antennas. But like this circuit can just as well be used as a sensor readout circuit, for instance in a spectrometer for a fiber Bragg rating sensor, or for an automotive sensor network that's fiber based or optical based. And even some of the functions needed for LiDAR could be implemented in such a circuit. It could be useful for biomedical application, not as a sensor itself, but as the readout circuit. Or it could be used for optical coherence tomography, which is very important for ophthalmology, dermatology, and dentistry. So there's quite a lot of functions that could be used. A last set of functions, for instance, could be for security. You could do optical hashing functions or optical proof of work blockchain functions, or even quantum key distribution. So does such a chip give us the one chip to rule them all? Well, on paper, yes, but it has the same type of drawbacks that you get from programmable electronics. These can be large chips and therefore expensive to make. The many elements make them less efficient, also in power consumption. But they have a big benefit in terms of cost. If we just look at the cost model for such chips, well, you have wafer scale production, and then in the end you end up with a customer. Now, in the case of an application-specific circuit, all the costs end up with the customer. However, if you have a general purpose chip that can be used by many customers, that means that a lot of the costs can now be split. All the non-recurrent engineering costs are shared by the many customers. So where are these costs? Well, you have the chip fabrication, like the silicon photonics and the driver electronics. These are largely non-recurrent engineering costs. While the packaging and the optical I/O is usually, at least at this stage, quite proportional to your number of chips. So if we look at, for instance, 3 different types of chips, like an expensive one in blue, a medium scale one in green, and a cheap one in red, then you see that the cost per chip obviously drops as you fabricate more chips. Now, if you take a programmable chip, which is larger and therefore more expensive, you see that these costs for the programmable chips are more expensive. However, if these programmable chips are fabricated in much larger volumes, then you see that the cost actually drops. So if as a customer you only buy a low number, but they have been fabricated in large numbers, that means your cost per chip is cheaper. And that means that for prototyping at smaller volumes, these programmable photonic chips can be essentially cheaper than an application-specific circuit. On top of that, you have a very strong benefit of programmable photonic chips. You have a much shorter development time. If your development time essentially from wafer to chip is typically on the order of 6 months to a year if you have to make a new chip, the programmable photonics chips cut this supply chain in half. And the expensive wafer fabrication, which takes a lot of time, can be done up front. So if you rely on off-the-shelf programmable photonic chips, your lead time for starting to develop a new application is shortened with many, many months, and a lot of costs are being eliminated. So this is the key value proposition of programmable photonics. You essentially can allow rapid prototyping and development for a wide array of applications. And that's important because that creates a model that we now see in electronics. That's one of the things that made electronics so accessible. Of course, this is still in its infancy. The first prototypes of these chips have been fabricated, but there's a lot of challenges to make this scale. We need to get the loss and power consumption down. We need to get the control electronics and the control algorithms there to configure these large circuits. But the economic benefits of being able to prototype this faster and essentially lower the adoption threshold for integrated photonics creates enormous opportunities. I mean, we could get the maker community enthusiastic about manipulating coherent light on a chip. And then at that point, it's totally unclear how many new applications we will see for integrated photonics. This brings me to the end of my introduction or tutorial on programmable integrated photonics. If you want to know more, there's a Nature paper which we've recently published, which gives you a fairly decent overview of what we've been, or what is all out there in the field of programmable photonics. And then the book, if you really are into heavy reading, the book by José Capmany and Daniel Perez goes into much more depth about all the different parts in programmable photonics. There's also a recent large review paper as well by José Capmany and Daniel Perez. Finally, if you're interested in the cost model that we've used here to calculate whether photonics, programmable photonics has benefits, I would recommend this paper in the JSTQE journal from last year. Okay, then I end here, and I just want to thank all the people who helped demonstrating this work, and the European projects Photonics Forum and MORPHIC for helping to fund our research. Thank you.